Right on with Professor Jeff Tallon, Professor Jeff, who is a distinguished physicist, Professor of Physics at Victoria, and he will now be speaking to us. Sorry, I haven't got the topic here, I left it back in my the fire in the equations. Okay, well, we look forward to that.
I'm a physicist, as was mentioned, and I really don't think it's possible for a physicist to play his or her trade without mathematics. So I'm going to work my way towards talking about mathematics and some of the underlying implications. And of course, my title is a quote from Stephen Hawking. The breath of fire in the equations. He asked the question, who or what puts the breath of fire in the equations that makes it possible for a universe to exist?
Excuse me, Jeff, could you move the microphone forward so you can speak to it? Thank you very much. That's great.
Okay, how's that?
Thank you, that's great.
I have been in meetings like this where the practice has been to even ridicule, poke fun at the atheists. And what I want to do actually is to be positive and to select a number of important statements that some of these people have made that I fully agree with, and my title is one such example. And I just want to mention this from Richard Dawkins because it's something that I very much believe to be the case. The existence of God is in part a scientific question. If you are a traditional evangelical Christian who has the view that God created, when Peter was talking about creationism, presumably he was talking about young earth creationism, but I certainly hold that God is responsible for the creation of the universe, this wonderful universe in which we live. If God has acted, even if just at that first moment of the Big Bang, but also as Christians claim that God has acted in history, then that's a testable activity that hopefully one can bring to bear certain scientific tools to address that question. So I agree completely with Richard Dawkins in this respect. The question of whether there exists a supernatural creator, a God, is one of the most important that we have to answer, and I say yes to that. And I think it's a scientific question, and I say yes to that also. And some of these aspects will unfold in what I have to say. Okay. One of the things that's emerged in the literature is the idea, not creatio ex nihilo, but factor ex nihilo. In other words, the occurrence of everything that we see in the universe spontaneously occurring out of nothing. And there are a number of examples. Perhaps the best known is Krauss's book, The Grand Design. A universe from nothing, where of course the claim is that a universe and many universes can spontaneously generate out of nothing. The Grand Design, Hawking and Lodinoff, where there's this rather interesting statement. If there is a law such as gravity, the universe can and will create itself from nothing. We'll come back to that in a moment. And of course it echoes, doesn't it, the picture, the story that was generated much earlier through evolution. Life does not need a creator. It can create itself spontaneously, beginning from abiotic processes, starting from, if you like, inorganic and progressing towards organic. But there are really huge challenges associated both of these assumptions. In the first instance, Einstein, Crick, Wigner, very well-known statements that they made about the universe, about life, about the capacity of mathematics to describe the universe. they all came up with this word miracle. It's some kind of miracle. And it's so easy in talking about a universe that appears spontaneously from nothing to overlook the fact that everything out there, the universe and life itself, is so spectacularly complex and spectacularly improbable. And I'll talk a little bit about some of that, but let's just go back to this statement here. The arrow show up here. Hawking and Mlodinow. If there's a law such as gravity, the universe can and will create itself from nothing. And of course there's a circular argument there, isn't there? Because gravity, what is gravity? Well, the general understanding is it's mediated by gravitons. We can say pretty precisely what the properties of a graviton is. It's got no mass, it's got integer spin, and it travels at the speed of light. I'll say a little bit more about that later. That is certainly not nothing. Okay, if you have to have gravity operating through the interaction of gravitons, then that is not nothing. That is not the universe creating itself spontaneously from nothing. But we can actually say more, because gravity is associated with the interaction of massive bodies. It operates by virtue of the distortion of space-time. That's the way in which the force works. So we're now presupposing massive bodies, we're presupposing space-time, and so it goes on. Moreover, the general understanding is, and Stephen Hawking talks about this a lot, there will ultimately be a theory of everything. There is a theory that integrates electromagnetism, the weak nuclear reaction, and the strong nuclear reaction. All we're waiting for is to integrate gravity in this picture. And it is generally understood, almost universally understood, that ultimately there will be this theory of everything where gravity at certain very high energy levels becomes indistinguishable from electromagnetism, from the weak nuclear reaction and the strong nuclear reaction. To describe all of those, we need 29 particles, and the graviton 30 particles. All of this to describe gravity. And it seems to me that that is the universe in which we live. So, if there's a law such as gravity, means if there is a universe like the one in which we're in, then the universe can and will spontaneously create itself from nothing. If you have a universe, hey presto, you have a universe. And that's the problem. And it illustrates to me a level of naivety that can come through from brilliant people when their statements are driven ideologically. And of course I have to watch that with myself, that coming from the other end of the spectrum, and very definitely ideologically driven, that I don't make the same mistakes. So, just now returning to this colossal challenge that I refer to, and the acute improbability of the universe. So this is a kind of a summary of the universe. This is a cosmic microwave background as you look out into space in all directions. That kind of summarizes the entire universe, and it's like looking back to 300,000 years out from the first moments of the Big Bang. These are actually fluctuations on a scale of 1 part in 100,000, so these are very minute variations that exist in the cosmic microwave background. But everything that we look at in relation to the universe tells us that this is incredibly finely balanced. It sits on a knife edge of improbability, and if anything had been just slightly different, the whole thing would not only topple, it would never have existed in the first place. And just to summarize this, here's a statement from Frank Tipler. Some of you will know the book by Barrow and Tipler. It is the classic publication of the anthropic principle, and Richard Dawkins refers to it, and Krauss refers to it, and Stephen Hawking, and many, many others refer to it. It's a brilliant exposition of what is known as the anthropic principle. He says, when I began my career as a cosmologist some 20 years ago, I was a convinced atheist. I never in my wildest dreams imagined that one day I'd be writing a book purporting to show that the central claims of Judeo-Christian theology are in fact true, that these claims are straightforward deductions of the laws of physics as we now understand them. I've been forced into these conclusions by the inexorable logic of my own special branch of physics, which is cosmology. Okay, so what we know about the universe around us is that it sits very close to what's known as the critical density. It's within about 0.5% of, as I say, the critical density. If it were more compacted, more dense, then everything would have just collapsed back into a big crunch. If it was slightly less dense, it would have gone on expanding forever, and galaxies would not have formed, and stars would not have formed, and so on. But as you go backwards in time and the universe shrinks, that critical knife-edge balance gets more and more critical. And in the first moments of the Big Bang, the critical density has to sit at something like 1 part in 10 to the power 55. As I say, that's 1 in 10 billion, 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 billion. And it's an astonishing discovery that's been made in the last 50 years. When we look at the first moments of that Big Bang, the universe was extremely hot. We refer to the hot Big Bang theory. There's the temperature, 10 to the power of 32, so whatever that is, 100,000 billion, billion, billion degrees Celsius. And the important thing is that that's a huge compaction, a huge energy density, a huge available energy. And the kind of inverse of available energy is entropy. So it's an extremely low entropy state. Penrose, who was the PhD supervisor of Stephen Hawking, worked out, he makes this famous statement, how accurate does the creator's aim have to be to get a universe with the properties that it has in those initial moments? And he comes up with this bizarre number, 1 in 10 raised to the power of 10 raised to the power of 123. Now, it's such a big number, the universe isn't big enough to write it out in normal notation. But the key point is that it's highly, highly, highly improbable that our universe would have started in that way. And then we know, I think I've talked in this very place about this particular issue. Empty space is not empty because spontaneously fluctuating in and out of existence are these particles called gluons, which bind together the nuclei within an atom, within the nucleus of an atom. And you can work out on the basis of that so-called vacuum fluctuation what the contribution to the cosmological constant is. This is Einstein's biggest mistake. He described it as introducing a cosmological constant, but it now appears to be very much needed in general relativity. And you come up with a number of about 10 to the power of 120 for the cosmological constant. We know this constant to be of the order of 1. So something else that is unknown to us has got to balance that constant of 10 to the power of 120 exactly in order to come back to the value 1. So these are just a few of the examples. I could go on and give you 18 or 20 other examples of the incredible fine balance that exists within the universe, and hence my picture of a finely balanced universe. The proponents of spontaneous creation of a universe, out of its own accord, have to contend with these huge improbabilities and a very special character of the universe that exists. When we turn to the biological world, we find very similar things. Biology is mediated by virtue, on the whole, of proteins. Proteins are these extended sort of chain-like molecules, and along their length they have amino groups. And the particular sequence of those amino groups determines the way in which that protein will fold. And the distinctive folding of the protein and active sites within that folded protein what activate metabolism and so many other activities that occur in molecular biology. The shape of that bending and folding is absolutely crucial. And of course, this is all coded for by the DNA. So 3 of those links across the double-stranded helix, so-called codon code for a single amino group, and the sequence of those amino groups, of course, is given by the genetic structure or the genetic code that exists there. It's interesting, Stephen Freeland, when he was at Cambridge, looked at all the possible codes that could exist. Now, in fact, there are multiple billions of different codes that could exist for coding for proteins. And he simulated these and found that the natural code was the least error prone in 100 million other possible codes that he investigated. And you have to ask, how did this come about? It's extremely difficult to work out how something like this could come about simply by virtue of selection and mutation and variation, because you change one part of the code and you change the entire suite of proteins that are generated. The human body, something like 100,000 different proteins. But then when you look at the process for this translation of the code to make the protein, it's incredibly complex. So the first thing is the double helix is opened up and the code on a gene is read by polymerase. Now I show you here a shorthand depiction of just one element of polymerase. There are 18 separate components in polymerase, and this is just one. The sequence is read off, a copy is made, a negative copy, if you like, is made of the code, and that's transfer messenger RNA, which then passes out through the nuclear pores in the nuclear sac. This fellow here is fascinating in itself because it requires 1,000 proteins to make up just that nuclear pore. And it only lets through certain desired traffic. Not any old molecule is going to be able to pass through this nuclear pore. And then it's read off and translated into proteins by the ribosome. And this is a little miracle in itself. The ribosome, every cell has got 500,000 of these ribosomes, and they will take transfer RNA here. So here's something that matches the codon, those 3 legs of the chain, and at this end here is the amino group, which is transferred onto the growing protein. For every amino group that comes in, one of these transfer RNA molecules has to be synthesized, has to come into the ribosome in order to add just one additional component onto the growing chain. This particular protein here is hemoglobin, which makes up the red blood cells, and it does so at an incredible rate, 100 trillion hemoglobin molecules every second in the bone marrow. And of course, we're very familiar with the end result. I can't help thinking of David's statement. He knew none of this, but he understood this instinctive, "You, Lord, created my inmost being. You knit me together in my mother's womb. I praise you, for I am fearfully and wonderfully made." This ribosome itself consists of some 18 proteins and an even larger number of RNA molecules. It needs 200 other proteins to synthesize that ribosome. And so you can see the chicken and egg problem, can't you? It requires proteins in order to synthesize proteins. And how on earth all of this kicked itself off is unknown to science. I went yesterday with Mary to Body Worlds Vital. Who's been to this down at the waterfront? It's really fascinating. And as you come out at the end of this, So it's the human body in which the muscles and the nerves and the veins have been plasticized by a particular process, and you can see the skin stripped away, and you can see the just amazing structure of the human body. And actually, when you think it all comes from a single cell in the mother's womb and ends up with this utter, unbelievable complexity, it's amazing. But this is what Gunther von Hagen says about this. He's the one who originated this exhibition. The older I get, the more I feel that life is extraordinary, a miraculous exception amidst the gigantic universe in which the absence of life is ordinary. But you know, one of the things that we've found in cosmology is that the universe has to be as huge as it is and as old as it is for us to exist. There's a great paper in Nature that addresses that very topic, written by Martin Rees, who is the astronomer royal. But it's also, I need to keep track of time here, a rational world. And of course the rational world that we, as academics, as human beings, engage with is through our brains, 100 billion neurons. But that's not what really does the business. It's the interconnectivity, the dendrites that connect somewhere between 20,000 and 100,000 interconnections for each dendrite. So that in total you've got 1.5 billion dendrite connections, and if you work out how rapidly these grow within the infant, it's phenomenal. It's about 8 billion per minute that are laid down. But that's not the only thing. You know, if we compare this with a computer, in a computer, each of the transistors in a computer are essentially identical. But one of the things that's been found in the last year, maybe last 18 months, is that each neuron is genetically and epigenetically different. And this is an essential aspect of the functioning of the brain. And I like to think how efficient the human brain is. You can go through all the calculations yourself and come up with a number that the human brain is 4 billion times more energy efficient than the equivalent number of supercomputers, and it's 1.5 billion times less carbon dioxide producing. And I worked out the methane equation. It's also a mathematical world, isn't it? We're familiar with Einstein and the idea that he came up with an equation of general relativity. There it is, and this fellow here in the middle, this lambda here, is the cosmological constant. And of course, that little equation, constructed more than 100 years ago, contains within it the notions of the Big Bang, black holes, gravitational waves, and the fact that gravitational waves travel at the speed of light. Black holes not contemplated until 50 years after that equation was written down. Gravitational waves not discovered until 100 years after that equation was written down. The demonstration that they travel at the speed of light would be familiar. Last year, 17th of August 2017, an observation was made at LIGO of the collision of two neutron stars and the huge pulse of gravitational waves that emerged from that. Now, the thing about this experiment was that it was also detected optically. Gamma rays were detected. Gamma rays are photons, just like light, and they travel at the speed of light. This event occurred 130 million years ago. Light and gravitational waves arrived separated by only 1.7 seconds in 130 million years. So gravitational waves travel at the speed of light, accurate to 1 part in 2 million billion. It's one of the most accurate measurements that's been made by humankind. But you see, that little equation somehow encapsulates in it reality, doesn't it, in shorthand. But the key thing that I want to say is that It contains reality, but it does not create reality, as our authors, as Krauss, for example, is suggesting. Now, back in the late 80s, early 90s, I worked in higher dimensional matter in higher dimensions. In fact, I was able to do this work in any arbitrary dimension. That's integral. It looks a bit complicated, but in fact it can be done for special systems like argon, and one can describe melting, for example. Here's the melting temperature, Tm. Here is the pressure, so one can describe the effective pressure on melting in d dimensions. Here, this d is the dimensionality. So the fact that I can write down an equation in d dimensions does not create a d-dimensional world. It will never, it doesn't matter how much I manipulate that equation or how many people play around with that equation, it will not create a d-dimensional world. So as I said, mathematics contains reality, but crucially, mathematics does not create reality. And Stephen Hawking beautifully summarized this by asking the question, what is it that breathes fire into the equations and makes a universe for them to describe? He goes on and says, science does not answer this question, science cannot answer this question. And to kind of illustrate his point in his own quirky way, he said, why does the universe go to all the bother? Okay, so I want to draw things to a close now, based on some of these thoughts. It remains a mystery, not only as to how mathematics works, but also as to how our universe came to exist for mathematics to describe. The Christian position that God created the universe is entirely consistent with Hawking's question. Indeed, I would go so far as to state that the Christian view of creation is necessitated by Hawking's question. In a self-contained universe, effect always follows cause, but in the singular moment of the Big Bang, in which no prior space existed and no prior time existed, physical or temporal cause is absent. Cause and effect break down, and the only solution for this is for the causal origins of the universe to lie outside of this universe, namely by the purposeful action of the Creator God. Hawking's question stands unanswered by science. What is it that breathes fire into the equations and makes the tangible, toe-stubbing, existential reality of the universe? And if, he asserts, science cannot provide the answer, then we must turn from research to revelation to find one. And the Bible brilliantly and succinctly declares in its opening sentence, in the beginning God made the heavens and the earth. And these words are repeated throughout its pages like a tolling bell, calling all mankind to awe, worship, and commitment. As for Ezekiel in the valley of dry bones, God breathes into the dead, dry bones of mathematical possibility and makes them living, breathing, organic actuality out of nothing. And these words suggest so much more than a mere capricious, invented whim of the Creator. They tell us that the creative act was purposeful, the beginning of a story that is intended to unfold through the actions of humankind by the exercise of their free will, for good or ill. A story which requires the eventual redeeming intervention of the Creator, who resolves in the only way possible to undo the damage done by that human free will exercised so wantonly and selfishly. Why does the universe go to all the bother of existing? Because it was spoken into existence by a Creator whose prescient eye saw you and me before time began, and who desired to know us.